In this video, we're going to do a few more problems related to writing net ionic equations. Before we do that, let's just recap what we saw in the last video. We saw an example of a net ionic equation being written. Our reaction was the NaClAq plus the AgNO3AQ produces AgCl solid plus NaNO3 aqueous. And so prior to the mixing of these two beaker contents with the sodium chloride dissolved in water and the silver nitrate dissolved in the water, the ions were just kind of swimming around freely, surrounded by water molecules. Then when we mixed the two beakers together, what remained swimming around was the Na plus and the NO3 minus. In other words, they weren't really part of a reaction. They didn't make anything new. They're still swimming around like they were before. But notice what is new is that the silver and the chlorines got together and became insoluble because they have such a strong attraction for each other. And most likely because they are relatively small ions, especially our silver here. So that's going to be a solid and come out of the solution. You can separate it from the solution, but essentially what really took place here is that the silver and chlorine got together. The Na and the NO3 just kind of stayed dissolved in water, surrounded by water, and didn't change much. So if you're writing a net ionic equation for this, essentially what you'd be doing is you'd be removing, let's remove this here, you'd be removing your spectator ions, which are your sodium and your nitrate. And by doing that, you write your net ionic equation, which only really shows what's happening to form the precipitate. The other ions are still there. We just don't really focus on them because they're not the main players involved in this reaction. So let's go ahead to our handout and do a few more practice problems. As I mentioned, it's great for you to try these yourself first and then to check your work with the video. So here we have a reaction of lead nitrate mixed with potassium iodide. So our reactants are the lead 2 nitrate, which is PbNO3 2, and that's aqueous. And then we also have potassium iodide. And so we're going to write a reaction for this, lead 2 nitrate, aqueous, plus potassium iodide, aqueous. We'll do our double displacement and we'll get KNO3. Now remember, nitrates are essentially soluble. We can go back and look at our table anyways, but we know that. And then we have PbI2. And so we just need to verify the PbI2 to see if it's soluble or insoluble. So potassium nitrate we said was soluble. And that makes sense because potassium's here, nitrate's there, soluble. Lead iodide, so lead 2 iodide. Lead's over here, iodide's over here. Iodide wants to be soluble, but lead wants to be insoluble. Lead's higher up than iodide, so lead wins and it is insoluble, and we have our precipitate there. So let's go back and add that as a solid. That means there is a reaction. And we need to make sure it's balanced. So we have 2 iodide ions on the right side. On the left side, we need 2 as well. And we need to put a 2 here to make 2 potassiums and 2 nitrates. And so now everything looks nice and balanced. So this is a balanced equation. It doesn't show what's really happening in the beakers. It doesn't show that these are actually swimming around in water as aqueous substances. So we're going to write a total ionic equation to illustrate that. So as you can see over here, we have 1 lead. And that lead is a 2 plus because that's what it said in our question, Pb2. So Pb plus 2, aqueous. Plus we have 2 nitrates here, 2 NO3s. And they are a charge of -1 each. And don't forget they are aqueous because they're dissolved in water. Plus we have 2 potassiums, 2K plus 1 AQ, plus 2 iodides, because there's a 2 there, coefficient of 2. So 2I minus 1 AQ. And that's going to produce, we can dissociate our KNO3s. So we get 2K pluses here. Plus we have 2 nitrates, 2 NO3 minus 1, plus 1 PbI2 solid. We don't separate the solid because it's insoluble. It does not dissociate. So there is our total ionic equation. To find the net ionic equation, we need to find the spectator ions. So which ones are not really doing anything, which one essentially appear on both sides unchanged. So spectator ions. In other words, which ones are not in our precipitate? So our precipitate is PbI2, so K is not in our precipitate, and it appears on both sides. And then nitrate is not in our precipitate. and appears on both sides unchanged. So our spectator ions are K plus 1 and nitrate minus 1. So to write this as a net ionic equation, we simply rewrite the ions that remain. So Pb plus 2AQ plus 2I minus 1AQ produces our precipitate of PbI2 solid. And everything is balanced. You'll notice you have 1 PB, 2 I's, 2 I's. And then this is an overall charge of 0 because we have plus 2 and minus 1, but there's 2 of them. So that's plus 2 minus 2, 0. And it's 0 on this side as well. But this is our net ionic equation. The other ions, as I mentioned, are still present, but they're spectators. They're still swimming around in water in much the same way they were before. They didn't commit to anything new and form a precipitate like the lead and the iodide did when they came together to make lead iodide solid, which is our precipitate that formed. And this is actually the demonstration that you would see in the presentation with the yellow precipitate forming. This is the PbI2 that forms. It's a yellow precipitate. So hopefully you tried this on your own and you marked yourself and assessed yourself as you went through this. Let's try the next one. Try it on your own first, and then assess yourself to see that you're on the right track. So we have sodium chloride mixing with calcium bromide. So let's write out our reactants to understand sort of what's going on here. So sodium chloride is aqueous here, and we have a solution of calcium bromide as well, CaBr2. And so that requires you to remember how to do crisscrossing, of course, and that's aqueous. And so we'll write a balanced equation. So we have NaCl AQ produces calcium bromide AQ. Or not produces, reacts with calcium bromide AQ. So sodium chloride reacts with calcium bromide AQ to make, we'll do our double displacement and we'll get calcium chloride, CaCl2 AQ. Actually, I don't even know that yet. I have to go back and double check. So let's write CaCl2. We'll go check in our table after. Plus NABr. So let's go check NABr and CaCl2 to see if they're aqueous or if there's a precipitate. So we had NABr. Let's erase this so we can see what's going on. So Na and Br. NABr is going to be soluble because Na wins, so we know that. And the other one we had to check was calcium chloride. So calcium's over here, chloride's up here, chloride wins and is also aqueous. So this is interesting. In this case here, we have two substances that are aqueous. And it's not that there's a neutralization reaction where water is made or one of these breaks down to make the gas in water. So this is clearly a case where there's no reaction because nothing new was formed. There was no new precipitate. These are all just swimming around in the same way they were before, just in the same beaker now. But no one connected to each other, made a precipitate. Nothing really changed. So this is a case of no reaction. But I'm going to show you why that is by attempting to make a total ionic equation anyways. And then a net ionic one. So let's make sure it's balanced. We need a 2 over here and a 2 over here and a 1 and a 1. And now I think we're balanced. So let's separate. Let's dissociate. So we have 2Na plus AQ plus 2Cl minus AQ plus our calcium plus 2 AQ plus 2 BRs. And that will produce, we can dissociate everything here basically. So our calcium plus 2 AQ plus our 2 chlorides AQ, and typically would have a precipitate to leave alone, but in this case there's no precipitate. So we have 2 sodiums here plus our 2 bromides AQ. That's an AQ there. And so now we have to go find our spectator ions. So we look at what appears on both sides unchanged. Well, if you look here, the Na plus 1. That's plus 1, by the way, and negative 1 here. So Na plus is a spectator ion. Also the chlorine. So chlorine minus 1 AQ is a spectator ion. Then you'll notice, oh look, there's no precipitate, so this calcium appears on both sides unchanged. So this is also a spectator ion. And then this too, the bromine or bromide for ion, also appears on both sides unchanged. So everything here is a spectator. Nothing is changing. Essentially, when you're making your net ionic equation, I'm just going to cancel this out, everything cancels out. And so because everything cancels out, we say there's net no reaction. So that's why we said in Unit 2, when you have two aqueous in that situation, there's no reaction because the ions are still just swimming around as they normally were. No one committed to a precipitate. No one made anything new. They're just swimming together in one common beaker. They were in two separate beakers before, here and here. Then we mixed them together. Now they're all swimming together in the same beaker, but they're just saying, hey, I'm still sodium ion. I'm still chloride. I'm still bromide. I'm still chloride. I'm still calcium. We're not making precipitates. Everything's the same except, there's a few more of us in here. That's basically it. And so when you have a situation like this and you were to try to write a total ionic equation, everything cancels out. Everything's a spectator. So in your net ionic equation, there really is no net ionic equation. There's no reaction there. So when you get a question like this, if you get this, you can simply write no reaction after you write your reactants out. But if I ask you to explain why that is, you can simply show me a total ionic equation, show me that everything is a spectator, and as a result of that, there's no net reaction that occurs. So net no reaction occurs because everything is a spectator ion in that situation. So that was just to show you what happens when you have a spectator ion, when everything is spectator ion and there's no precipitate that's made. This last one is a sort of challenge style question. There is a video there that goes over it, but I will go over it in this video as well, just to give you a different perspective, my perspective of it. But again, both videos are fine. They'll allow you to understand the information. So here we have a solution of sodium hydroxide. That's one of our reactants, aqueous. And it's going to be reacting with this phosphoric acid, which is H3PO4, AQ. And so we're going to write that out. This is a neutralization style reaction. So we have NaOH, AQ, plus H3PO4, AQ. And we're going to do a reaction. It's a double displacement. Sodium goes where H was and H goes where sodium was. And so we'll get essentially our H2O liquid plus our Na3PO4. And if you go look in your table, Na3PO4 is aqueous. And we need to make sure everything's balanced. So to balance this, we might want to put 3 over here and a 3 over here. And now I believe it's all balanced. Let's just double check though. 3 sodiums, 3 sodiums, 3 OHs, 3 OHs, 3 H's, 3 H's, 1 PO4. Great. So now we have to go and separate the ions. And we're pretty good at that typically. So we know there's 3 here. So that's 3 Na plus AQ. Plus there's 3, so 3 hydroxides, AQ. But the tricky part is this part here. Normally we say acids do ionize. You can separate them into their ions, but only if they're some of the strong acids that are listed above here. So only these acids that you see over here will be able to form the ions. In the hint that I had provided, the H3PO4 is what's called a weak acid. And so because it's a weak acid, we cannot ionize them like that. And we'll learn more about what that is later. For now, just kind of plant the seed as to weak acid. I gave you that hint. So we're simply going to leave it unionized. So H3PO4 AQ produces, now water's a liquid, so it does not separate into ions. That was one of our rules as well. So 3H2O liquid plus this one can ionize, dissociate, I should say, because it's ionic. So we have 3Na plus 1 AQ plus the PO4 3 minus AQ. And so what we need to do now is go take a look at which ones are spectator ions, which ones appear on both sides unchanged. So really the reason this is a challenge is because you have to understand that this is an aqueous, it's an acid. You'd think you could separate it into ions very easily, but it does not. I mean, some do, but not a lot. So we can't justify writing it all out like that. So we have to pay attention to the fact that it's a weak acid. So it looks like the Na plus appears on both sides unchanged. So that's definitely going to be a spectator ion. And I believe that's about it. So we can rewrite everything now. We have 3OH minus 1AQ plus the H3PO4 AQ produces 3H2Os liquid plus PO4 3 minus AQ. And it looks like everything's balanced because in this 3H2O, just to rewrite it in a different way, it's 3HOH. You have 3 OHs, and that's what you have here. You have 3 H's, and that's what you have here. And then for phosphate, you have 1, like that. The charge looks balanced as well because they have 3 minus here, and 3 times minus 1 is 3 minus. And so this is our net ionic equation for the reaction between sodium hydroxide and phosphoric acid. Just a reminder, net ionic equations can be written for a variety of chemical reactions. It doesn't just have to be for double displacement. You can do it for single displacement as well. So a quick little example, suppose we had Na solid reacting with aqueous calcium chloride. You would look at your single displacement table and you'd notice that in my single displacement table, sodium can kick calcium out. And so calcium will be a solid. So this is not the ion, it's just regular calcium solid, so it charges 0. Plus crisscross between sodium and chlorine, which is NaCl. And if you look at your solubility table above, NaCl is aqueous, right? Solubility table, back up here, NaCl is aqueous because it's soluble. And so you have that written out. And you can write this out as a total ionic equation. So you can write your Na stays the same. There's no charge there, just the sodium metal. Plus, well, let's make sure it's balanced first. Actually, I didn't do that, and that's bad. I should have done that. So 2, okay, now we're balanced. There you go. So 2 Na plus 1 calcium, aqueous, plus 2 chlorides, aqueous, produce 1 calcium solid plus 2 Na plus aqueous plus 2 Cl minus aqueous. So this is my balanced equation. This is my TIE, total ionic equation. So let's go identify the spectator ions. So we can write a net ionic equation. So spectator ions. What appears on both sides unchanged? Well, it looks like we have the chlorine, or chloride, I should say. So that's a spectator ion, Cl minus 1 AQ. Everything else changed in some way. The sodium is now sodium plus 1, and the calcium plus 2 is now calcium solid. So they appear on both sides, but they're different. So in this situation over here, my net ionic equation would be whatever's not canceled out. So I get 2Na solid plus Ca plus 2AQ, and that's going to produce some calcium. That's solid plus 2Na plus 1AQ. My charges are balanced because there's two pluses there too, and these are 0 and 0. And my amount of atoms are balanced. So I have one calcium, two sodiums, two sodiums. And this would be my net ionic equation for a single displacement reaction. So the sodium is reacting in some way with the calcium plus 2 to make some calcium and some plus 1. And as you can probably guess there, chances are there's some kind of transferring of electrons happening in some way, shape, or form from somewhere along the line. But the chlorine essentially stayed as it was, dissolved in water, unchanged as its ion form. And that's why it's a spectator, and that's why we could do a net ionic equation. So you can do net ionic equations for a variety of reactions. We focus on double displacement for this unit, but understand that wherever you have ions, dissociation, ionization, you can look at the net story that's being told. So at this point, you'll be able to use solubility rules to predict precipitates in double displacement reactions. You'll be able to write balanced equations for those. You'll be able to convert those balanced equations into total ionic equations and then write net ionic equations by identifying the spectator ions. You also have a better understanding of the reasons why certain substances are more soluble than others using factors such as ion radius and ion charge. And then you also know how to do applications of precipitation reactions, for example, water purification, where you can trap a soluble substance in a precipitate to remove it by filtering it. And I do highly recommend that you watch the demonstrations and the other videos added in this lesson so you can get a better understanding of what precipitates look like. Take a look at the visuals to see what soluble and insoluble looks like and why certain times you might have no reaction versus a reaction when it looks like a precipitate has formed. So practice makes perfect when it comes to these problems. Do make sure you are practicing the writing of the ionic equations.